Okay, so let's talk about the outer planets. And their moons. We'll talk a lot about their moons. Today, we'll probably just cover Jupiter and Saturn because there's a lot to talk about. Jupiter and Saturn are both essentially solar systems of their own because they have so many interesting moons. And so we'll get to that. All right. So the planets beyond the asteroid belt, we will talk about the asteroid belt when we get to minor bodies in the solar system. Yeah. So the four outer planets, these are called the gas giants. Well, these two are called gas giants. These are ice giants. Some people include these in again, the boxes that we try and put things in as humans just don't really fit all the time.
Why does the storm keep on going?
We'll talk about that in just a second. So the giants. So this, anyone know which of the planets this is?
That's the one that's going sideways.
It's the one that's going sideways. Wilkes? It is Uranus. It is Uranus. It looks really dark blue, which Neptune is darker blue, but the way that you can tell is because it's sideways and the ring is quite apparent. So they are all mostly gas and ice. They are covered in very thick atmospheres. They all have rings. Okay, Saturn has the most apparent rings that you can see, but all of them have at least one ring.
Isn't Mars going to get rings?
Mars will have a ring in a few million years when it shreds Deimos. Yeah. And we can talk about how they create rings later, but they all have rings. They are very massive. They're much larger in size as well. They're more massive, but they're less dense. And that's because they're made out of gas and ice. But because they're so massive, they have a lot of pressure.
So they're the exact opposite of humans. Because the bigger the human, the denser they are.
Nope. Generally, the bigger the human, the less dense they are.
That was an insult to most guys.
Okay, so Jupiter, we'll start there. Has 317 Earth masses. It is primarily made out of hydrogen. It takes 4,332 days, Earth days, or 11 Earth years for the planet Jupiter to go around the sun. It rotates every 9.5 hours, which for a planet that is the size of Jupiter, to rotate every 9.5 hours, it's really moving, okay? And it has an extremely strong magnetic field. We'll talk about that in a little bit more detail in a second, but it is a truly massive in every sense of the word. Remember that when we talk about the solar system by mass, that the sun is 99.99% of the mass of the solar system, and that the other 0.01% is Jupiter. The other planets are essentially negligible. Okay? The other planets are so small in comparison to the sun and Jupiter that they account for less than 0.001% of the mass of the solar system.
How many Mars masses would fit in that?
Mars masses, about 900. Mars is about 1/3 the mass of the Earth. So, yeah, and you can see that its volume, 1,321 Earths, its volume is much higher than its mass in comparison to the Earth, meaning it is much less dense, but it is humongous in size. And you can see one of its moons here, and the characteristic banded clouds. Has anyone ever seen Jupiter with their own eyes through a telescope? If you have an opportunity to use a telescope to look at Jupiter, a decent one, you'll be able to definitely see the stripes in its clouds, and you'll definitely also be able to see at least 4 of its moons, which we'll talk about in a little bit. This is the symbol for Jupiter. I do not know what this is in reference to. I think it has something to do with lightning or thunder, but I do not know. Jupiter is the.
It looks like the number 4.
It does look like the number 4. Jupiter is, of course, the Roman god of thunder and lightning. Truly the king of our solar system. Okay? It is just so much more massive than anything else in our solar system. So the inside of Jupiter has a very intense pressure because it's so large. So remember that stars make fusion by pressing things together in their cores. Jupiter is very massive. It's not nearly mass enough to be a star, but it has a lot of mass. And when all of that mass presses in on the hydrogen near the core, it starts to behave like a metal. This is called metallic hydrogen, and it is extremely conductive. And we cannot reproduce metallic hydrogen here on Earth. If we were able to produce metallic hydrogen, it would be a very good fuel source, but we don't have enough pressure to do it in large scales. I think that it has been done one time, pressed in between 2 diamonds at like ridiculous pressure. Have you done research on this, Oliver? You seem to be. Yeah, I heard about that. Yeah, so in a diamond press, so 2 diamonds were pushed together really, really hard, and hydrogen was introduced between them. And the data seems to suggest that we created metallic hydrogen, but we don't know exactly for sure. It's very difficult to do. Yeah, Cameron?
So basically, if we were to eventually colonize this, the only thing that would pretty much be built in this would be a place to harvest metallic hydrogen.
You wouldn't build anything in the planet because
It doesn't have a surface.
It doesn't have a surface, but even going down into the clouds, like you could construct floating colonies in the clouds, but in the actual, once you go down into the clouds, the pressure becomes so ridiculous. Everything starts behaving very strangely. The gases start behaving as a superfluid, and it gets hot. It's just a mess. Wilkes, you had something?
Oh, I figured out what the symbol meant.
What the symbol means?
Either supposed to be Jupiter's thunderbolt or an eagle.
Or an eagle?
Yeah.
Well, it doesn't look like either of those things, but we'll just take their word for it, I guess. A thunderbolt or an eagle, I guess so. Okay, so the metallic hydrogen creates an extremely strong magnetic field, or what we call a magnetosphere. Magnetic field of Jupiter creates amazing aurorae at the poles. This is the aurora borealis of Jupiter, the northern lights. This is a real image. Beautiful, right? It's absolutely incredible. So here on Earth, we have the northern and southern lights because the magnetic field of Earth captures radiation from the sun and funnels it toward the poles, where the magnetic field actually, so the magnetic field is like a 2-sided, it's like a figure 8, right? And where the 8 connects is in the center the planet, and so those particles get funneled in to the poles, and you can end up with aurora like this. This is also a fantastic image. So we have, of course, the Great Red Spot. The Great Red Spot is a storm that is approximately 3 times the diameter of the Earth. You can see how disturbed the clouds are behind the storm. It is obviously very powerful. The bands on Jupiter actually are wind currents that run in opposite directions. And the lighter color, I believe, is a cloud layer that is a little bit lower down in the atmosphere, and the reddish orange stuff is a little bit higher up in the atmosphere. As you get closer to the poles, the clouds become more and more blue. That is because of the temperature. So the temperature is highest at the equator, just like here on Earth, is lowest at the poles. The poles, because they experience lower temperatures, actually, the poles of Jupiter are blue for the same reason that Uranus and Neptune are blue. And that is because they are cold, and methane starts to show up as frozen methane in the atmosphere at that part. Frozen methane, okay? So pretty crazy. Metallic hydrogen makes this extremely strong magnetic field. The magnetic field of Jupiter is so strong and it captures all of this radiation. Here on Earth, there are things called the Van Allen belts.
Oh.
The Van Allen belts are areas in between sections of the magnetic field on Earth where radiation gets trapped. And going through the Van Allen belts can be very dangerous. The only people to do it were the Apollo astronauts. And they're okay, but if you hang out there for a while, it can be really, really dangerous and detrimental. Jupiter, if you were to go through Jupiter's equivalent of the Van Allen belts, you'd be dead within a few minutes. The radiation is extremely strong. And that is because its magnetic field is so strong. This is also a problem that we encounter sending spacecraft to Jupiter, because as they go through, they get the radiation and it can ruin their computers. And so the computer has to be encased in a radiation shielding housing so that it doesn't destroy the computational abilities.
So did we send things to Jupiter?
We've sent multiple things to Jupiter.
How many of them died?
All of them except for one currently. There is one mission orbiting Jupiter. It is called Juno. And at the end of the class period today, we will look at some images from Juno, and they are mesmerizing. They are beautiful. And Juno does this insane, like, super elliptical orbit. It goes way close to Jupiter, and then it gets flung really far back out. The reason why they do that is because they want it to spend as little time in the radiation belts as possible. So it goes in really fast, gets really close, takes a whole bunch of pictures, and then goes back out and sends all the pictures back to Earth. So it's pretty cool. And we'll look at all those pictures, or not all of them, but a lot of them, and they are seriously like some of the most beautiful things that you'll see in all of astronomy. Okay, so the storms of Jupiter, these are actually 2 images from the Juno spacecraft. Storms of Jupiter, so the internal heat and the rotation, so we've got a whole bunch of heat. So if you took my Earth systems class, you'll remember that hurricanes are like heat engines, right? They run off of heat and they spin because of the rotation of the Earth. This is a similar thing that's going on Jupiter. You end up with these huge storms, okay? Yeah, yes. So these extraordinary weather patterns, you see each of these spots are storms. And each of these is probably a significant portion of the size of the Earth. So these are Earth-sized storms that are going on on Jupiter. Those banded clouds, like we talked about, are wind going in opposite directions. Repeat. Do they have eyes? Yes, they do. They spin just like Earth storms. The Coriolis effect, which is what makes storms spin here on Earth, is even stronger on Jupiter, and that is because its spin is so fast. So Earth takes 24 hours to spin, and Earth is small, right? Jupiter takes only 9 hours to spin, and it is much larger. And so that means that the cloud tops and the exterior portion of Jupiter is rotating really fast. So the surface of the Earth rotates at about 1,000 miles or 1,600 kilometers per hour. Okay, the surface of the Earth. We are all going that direction, pointing toward the mountains. We are all moving that direction at well, here at 45 degrees, we're going significantly slower. We're going about 600 miles per hour, 1,000 kilometers an hour. That has to do with the, size of the circle that we're making. Anyway, we are all moving pretty quickly. The outer layers of Jupiter are moving much, much, much faster, okay? And that creates this insane Coriolis effect. We have these very strong storms, the cloud tops, and again, we see that blue near the poles. So this is the southern pole here, and then the equator is really the kind of the rim of what you can see there. And then we have the north pole here of Jupiter, okay? So pretty amazing. They are humongous storms caused by spinning and the internal heat. And it is very hot in the inside of Jupiter. It's much hotter than Earth's core. I think it's like more than 10 or 15,000 degrees Celsius, but you don't really need to know that, okay? All right, so we need to talk about a few of the moons of Jupiter. We're going to talk about 4 of them specifically. There are 4 Galilean moons. 4 Galilean moons. Why would they be called Galilean? Yes?
They were counted by Galileo.
Yes. Galileo was the first human to see them. He saw them through his telescope. Interestingly, all 4 of the Galilean moons would actually be visible with the naked eye if Jupiter wasn't there. They're large enough to see from here if Jupiter was not there. But because Jupiter is there, it's so bright that we cannot differentiate the 4 small specks next to it. Ganymede and Callisto. This is Ganymede, this is Callisto. They are both larger than Mercury. So Mercury, being the smallest planet, is smaller than some of the moons of Jupiter. They are both very heavily cratered. You can see that here. Callisto is quite pretty, I think, kind of like a purple, dark purple color. Ganymede, this is actually ice on the exterior. We don't know a whole bunch about the ice and what's going on there. Liquid ice, or not liquid ice, water ice. But they're heavily cratered because these asteroids from the asteroid belt get disturbed by Jupiter's gravity, and they get pulled in toward Jupiter, and the moon just happens to get in the way before it hits Jupiter. So they come in and get smacked. Okay, it is very possible that both of these have liquid water under their surfaces. We don't know that for sure yet. It is very, very possible, however. Ganymede and Callisto. By the way, all of Jupiter's moons are named after Jupiter, like the god Jupiter, and his consorts. So, you know, Jupiter was, you know, kind of promiscuous. So all the ladies that Jupiter would hang out with, Ganymede and Callisto are two of them. Now let's talk about Io. Io is pretty cool. It is the third of the 4 Galilean moons. It orbits very closely to the planet. And because it orbits so close, it gets squeezed and pulled by the immense gravity. This squeezing and pulling creates a lot of heat in the interior of Io that leads to volcanism, a lot of volcanoes. So you can see these spots here. There's all these spots on the surface of Io. These are all volcanoes. You can also see this is a lava flow here. This kind of like bluish thing going on. You can see all sorts of lava flows here. And this right here is the real showstopper. This is a column of ash being ejected out into space off of the surface of Io. And so one of the probes that we have sent to Jupiter was looking in the direction of Io and just happened to see the sunlight striking this ash column. And for reference, this column of ash and dust and volcanic pyroclastic is going several hundred kilometers into space. If this was the Earth, the International Space Station orbits like right here. Okay? So this is being ejected out past where the space station orbits Earth. Okay? It's a pretty serious volcanic eruption. And this is not unusual. Io is constantly in a state of volcanic activity. And that is because of the amount, really Io is being torn and pulled and ripped apart. Eventually, its orbit will decay to pass what is called the Roche limit, that's R-O-C-H, at which point it will be shredded into a ring around Jupiter. The Roche limit is similar to spaghettification. You remember we talked about that with black holes? It's similar to spaghettification, that the side that faces the planet, it feels more gravity than the side that is away from the planet. And so it gets shredded into pieces. Io. I really like Io, the name. It's a really cool name, just 2 letters. Okay. And I saved the most interesting, I wouldn't say necessarily the best, but the most interesting of the Galilean moons for last. This is Europa. So these are 4 of Jupiter's 79 confirmed moons. Europa is completely covered in water ice. There is more water under this ice than there is in all of the oceans of Earth combined. Okay? There is more water on Europa, more liquid water on Europa than there is liquid water on Earth. This ice can be several kilometers thick in portions. Some of it is not quite that thick. Some of it's just a few tens of meters. You can see these cracks. These are cracks in the ice. Those cracks are red due to some stuff that comes out of the water. From what I understand, it's rust, iron oxide, similar to what Mars is covered in, but there's much to learn about Europa. So the same process that heats the core of Io warms the core of Europa, and this keeps the oceans liquid. So the oceans of Europa are kept liquid by volcanic activity on the quote-unquote surface underneath the quote-unquote surface, the crust that is under this water is volcanic. And so similar to hydrothermal vents here on Earth that heat these oceans and keep them liquid. Okay? Every once in a while, we will see geysers of water shooting out of the cracks and out into space. There is a very, very interesting mission called Europa Clipper that is set to launch in 2026. That is going to go to Europa and try and fly through some of those geysers and get a taste of what might be in the water.
That sounds pretty hard to do.
What?
That sounds pretty hard to do.
Well, it wouldn't be the first time that we have flown through geysers from a moon around one of the gas giants. And we'll talk about that when we talk about Saturn. One of Saturn's moon, the Enceladus. Okay? Pretty cool. Europa is a beautiful place. It is a very promising prospect for finding life in our solar system. I'd like to drill a hole in that ice and go ice fishing. See what nibbles on the hook. Yeah, Oliver. If there was one life form in our solar system, what do you think it would be on Europa, or Venus, or somewhere else? So you're asking me where would the most likely place for life to arise if it was just one place, and I can't pick all of the above? I cannot pick all of the above. I think that Europa is the best shot we have at finding complex life. So life that is multicellular. I think that Venus is a really good shot for microbial life in its atmosphere. I also think we'll talk about Enceladus with Saturn, has a really good shot as well. We're not going to talk about this. I'm going to skip over all this. This is more for like space exploration, but we've sent multiple missions to Jupiter. Right now we have Juno. Okay, but don't write this down. This isn't important for this class. Saturn. 95 Earth masses, 763 Earth volumes. Takes 29 Earth years to go around the sun, and it rotates every 11 hours. It is truly the crown jewel of our solar system. The first time that I saw Saturn through a telescope, through my telescope, through a telescope, I cried. It is so beautiful. I had bought my telescope in February. I was living in Logan, and Saturn didn't rise until like 2 o'clock in the morning during that time. So of course I stayed up until like 2:30 in the morning, and I drive out to the middle of the field in Logan, and I pull out my car, and this is in Logan, okay? Like, you think that Ogden is cold in the winter? Go to Logan, all right? It was, I think it was something like -20 degrees Fahrenheit, which is like -30 something degrees Celsius. And it was so cold. And it's really hard to operate the controls of a telescope with gloves on, so I had to take my gloves off. And I'm just like freezing, right? And I'm looking through my telescope, and I start crying, and the tears start freezing on my face and in my beard. I immediately put the telescope back away and drove home, but because I didn't want to die from hypothermia. But pretty beautiful sight, okay? The rings are something else, and when you see the rings, and you can see very much, you can see the division between the planet and the rings, and then with a good telescope you can also see this split in the rings. This is called the Cassini division. It is just really gets you. Okay. This is the hexagon on the northern pole of Saturn. It is really strange. We don't really understand why that is there. It has to do with the wind patterns on Saturn. You can also see in this image here, sorry, we have some aurora here at the southern pole of Saturn. Rotation is kind of a guess, so we think it's about 11 hours because the magnetic pole and the rotational pole are perfectly aligned. And so we can't really like see the magnetic pole being, usually the way that you measure the rotational period of a planet that's covered in clouds is by watching the magnetic pole get swung around, right? That's how we did it with Jupiter. That's how we did it with Venus. The magnetic pole is not perfectly aligned with the rotational axis, so it goes around in a circle. Saturn's magnetic pole is almost perfectly aligned with its rotational pole, so it's very, very difficult to determine how fast it is actually spinning, because the clouds don't really indicate that. The clouds are moving and shifting all the time. It is less dense than water. If you had a planetary-sized pool, you could float Saturn on the pool. It's very dispersed. It's not very dense. Almost completely hydrogen again.
As long as mass is condensed, how big would it be?
Depends on how condensed you're talking. Condensed down to like the size of the Earth.
Solid condensed.
Condensed to be solid. So let's say like the same density as Earth. It would be, I don't know, 5 or 6 times. No, wait, no, because it would be 95. There we go. It would be 95 times. Does that make sense? If it was the same density as the Earth, it would be 95 times the size of the Earth. Okay. Yeah. Moving on. The rings. It's kind of Saturn's thing, right? Besides the hexagon, but this is what everybody knows about Saturn, right? Is that Saturn has rings. They are really wide. So if you were to take a very long measuring tape and measure from the outermost ring to the innermost ring, it's about 70,000 kilometers.
Yeah, big.
However, it is really thin, only 10 meters. So it is 70,000 kilometers wide, but only 10 kilometers thick. So, or sorry, 10 meters, not kilometers, meters.
In comparison to us, how big is that?
That is about the height of the 3rd story of Da Vinci.
I wouldn't call that small.
Okay? It is not very tall.
The universal scale. But
Well, 70,000 kilometers wide, though. 70,000 kilometers. I mean, it's huge. It spans this huge area, but it is so just razor thin. And this has to do with rotational energy and how things flatten out when they are being rotated. The rings are named A through F, and there is the Cassini division here in the middle. You can see the shadow here of the rings on the planet. And you can see the band of the Cassini division where light sneaks through here. A is closest to the planet. F is the farthest away. Okay, they are, yeah, isn't that crazy? 70,000 kilometers wide, but only 10 meters thick. Okay, so I'm going to move on here. The moons. Saturn has 62 categorized moons. Only 53 of them have names. They differ greatly in size. Only 13 of these have a diameter that is greater than 50 kilometers. They also vary greatly in their coolness.
And then Saturn's ring right there.
Yes, so this is the ring here.
If the moon was, if our moon was to like approach it from the side, it would be cut in half.
No, it would not. It would it's not one continuous piece.
But like, could it just be bombarded?
It would be bombarded.
Line
Yes.
So much that it came apart.
No, I don't think so. Because even though it's not all that much stuff. It's quite dispersed.
If it went through the entire ring and just destroyed the whole, like it just
Everyone-
slowly enough.
So you got to remember that our moon was created out of a ring, and that's essentially what happened. Is that stuff went through the ring and just collected all of it. It wouldn't be cut in half. I know, bummer. It would just get bigger, but only slightly, because Saturn's ring has not very much mass.
and then Saturn would just eat them.
So how many moons do you see in this image? By show of fingers, how many moons do you see in this image? 3. Most people are putting 3. Daniel says 4. Daniel is correct. 1, 2, 3, 4.
I didn't know that big one in the background was moon.
So this is a little tiny guy. So there are moons that orbit inside of the rings, and they have a name, which we're going to talk about briefly here. Man, time flies when you're learning cool stuff. So 4 moons here. This is Titan in the background, which is the largest of Saturn's moons, looming in the background. This is Enceladus. This little guy is called Iapetus. And then there is little itty bitty tiny Pan. Pan is in the middle here.
If I stood on it and jumped really hard, did you get off of it?
Yes, if you stood on Pan and jumped really hard, you would have enough velocity to escape Pan's gravity completely.
How hard would you have?
Um,
Like as hard as you could?
you're gonna make me look up the escape velocity of Pan.
Yes.
Well, I'm just wondering, what about the next one? Did you jump off of that one?
Iapetus, probably not.
Oh, but you'd be close.
I don't know, maybe.
Maybe if you had like one of those long poles and you
Maybe.
roll out.
So these are the shepherd moons. So here's Pan, here again. Pan is a shepherd moon. Orbits inside of the rings, helps the rings stay in place. You can see where Pan has passed through here in this image. There is a tiny little disturbance pattern in the particles of the moon, of the ring. So this disturbance pattern has been created in the particles of the ring. Remember that the ring is not like a solid thing. It is many small pieces, most of which are in between the size of a grain of sand and like your head. okay? So these are really small little pieces that all orbit Saturn together. So you can see two shepherd moons right here in this extremely thin portion. I believe this is the F ring, which is the farthest out. The shepherd moons, they help control the orbits of the ring particles. Okay, I'm gonna go in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. So here's the discussion that I want to finish this class up with quickly. So we didn't get to finish all of Saturn's stuff, but where do we draw the line between moon and ring particle? Or
when humans feel like doing it.
because we have a shepherd moon here. I believe this is Pan once again. You can see the shadow that it's casting on the rest of the ring particles, which is pretty sweet.
Well, that is trippy crap.
Okay, but all of this stuff right here, all of this that makes up the ring, these are not solid. They are made of tiny little things. And so where do we draw the line? Because Pan is nowhere near spherical. It's a space potato.
Spherical?
No, it's not spherical. It's a space potato. Okay, it's like.
That sounds like an adorable, wholesome comic.
Yeah.
Space potato.
So is Iapetus. Only what was it, like what, 5? Second. Only 13 of these moons have a diameter of 50 kilometers or more. And of those 13, I don't think that all of them are completely spherical because they don't have enough mass to pull themselves into a sphere.
How much energy would it take to turn a planet into a cube?
Way too much. Okay, so the problem is, again, where do we draw the line? Saturn has a crap ton of moons, but many of them are very small.
What's the line between asteroid and
An asteroid orbits the sun, a moon orbits a planet. Daniel? Yes. So I want you to consider the Juno. You know what? I'm just going to pull up. There's a really great video. There's this guy.
of course I'm gonna be able to,
Well, the amount of work that went into this is crazy. He took images from, oh, good old ads.
for a second when you said that, I think
So these are images from Juno that have been stitched together and edited into a video. Also, I love the choice of music, really good. Isn't it just like, it's mesmerizing? Yeah, well, it is. Yeah, this is not in real time. This is sped up. You can find the same guy. His name is Seon Dorian, I think is his name. Has made a video of a real-time orbit of, I think it's like 90 minutes that as it passes by. But yeah, I mean, look at the clouds. You can see the details of these little amazing stuff. Oh, okay. It really is like, and you can see the disturbances that these large storms have made in the clouds. So I think that Earth is beautiful for sure. But when you see the clouds and the bands and patterns on the surface of the tops of the clouds of Jupiter, it's pretty amazing. Okay, I'll see y'all next time. Goodbye.